Okay, this video is about energy level diagrams and electron configurations. So, for both of these, there's 3 guiding principles and rules. So we have to follow the Aufbau principle, which states that when filling the orbitals, with electrons, you start with the lowest possible energy levels first. So the lowest N and L values. Fill the orbitals. Fill the orbitals in increasing energy until all the electrons are accounted for. Pauli exclusion principle. Pauli exclusion principle. This states that an orbital may be empty, have 1 electron, or at the most 2 electrons. And no 2 electrons can have the same 4 quantum numbers. So no 2 electrons can have the same 4 quantum numbers. So, for example, if the line represents an orbital, they can both electrons do not spin in the same direction. This cannot happen because this would mean that they both have an ms value of plus 1/2. So, one will spin up, one will spin down. That way they have 2 different ms values. The first 3 quantum numbers will be the same. They'll be identical because they're in the same orbital. Then the last rule is Hund's rule. Electrons in the same sublevel. A sublevel means that you are all of one type of orbital on an energy level, so all the 2p orbitals or all the 3d orbitals. But electrons in the same sublevel, for example, 2p orbitals is a sublevel on energy level 2, will not pair up until all the other orbitals in the same sublevel are half filled. So if we've got a 2p orbital, you won't have 4 electrons in the first 2 orbitals. They will not pair up. what'll happen, if you have 4 electrons, one will be in each 2p orbital on the same sub-level, and then the first one will double up, and so on, until they are filled. Energy level diagrams, the actual diagrams. Some textbooks show them as circles. I just draw them as a line, the actual orbitals. So, energy level diagrams show the order of the orbitals in terms of energy and the number of electrons present in each orbital. The quantum numbers and periodic table are used to develop the diagrams, so keep yours handy. So, at the bottom, the lowest possible energy orbital is the 1s. There's only one of them, so there's one line. The next highest in energy is the 2s orbital. So we're going to line it up with the 1s. Next highest orbital is the 2p's, and there's 3 of them. So we line them up just so. 3s is the next highest. Line it up with the other s orbitals. Then you have 3p. Line them up with the 2p's. Now, you would think that the 3d orbital would come next because it is the other set of or sublevel within the n equals 3 energy level, but actually 4s overlaps with the 3d orbitals and actually fills first. So the next one is the 4s orbital. Then it's followed by the 5 3d orbitals. So 4s fills before the 3d. Then after the 3d is the 4p. So this is how the energy levels fill. Now 5s will come next, followed by 4d, followed by 5p. So there's a pattern now. The s will fill before the d orbitals from the previous energy level. And of course, when you start filling them, you fill them from the bottom and you move up. So this is increasing potential energy. And your electrons go in. One spins up, one spins down. Some textbooks show a complete arrow. I just do a half arrow. You can do whatever you prefer. What I'd like you to do now is pause the video and draw the energy level diagram for oxygen. So example number 1, I want you to draw the energy level diagram for oxygen and all of its electrons. Okay, so oxygen has an atomic number of 8, so it has 8 electrons. The lowest energy level is 1s, so 2 go in there. Then you have the 2s, 2 go in there. That leaves me with 4 electrons. I've got my 2p orbitals, so 1, 2, 3, 4. There's my energy level diagram for oxygen. Now do the energy level diagram for nickel, for the nickel atom. So pause the video, write out your energy level diagrams, and fill them in. Okay, so nickel has 28 electrons. 1s, 2s, 2p, 3s, 3p. Okay. 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we've placed 18, so we have 10 more to go. Now, after 3p, 4s fills, then our 3d. So we've got 8 left to place. So 1, 2, 3, 4, 5, 6, 7, 8. So there's our energy level diagram for the nickel atom. Now we do energy level diagrams for our ions too, our anions and our cations. So an anion will gain electron. It'll gain electrons. And you just add the extra electrons into your energy level diagram. So let's say, for instance, fluoride, the fluoride ion. So fluorine has an atomic number of 9, so it has 9 electrons, but if you've made it into an ion, you've gained 1, so now we have 10 electrons to place. So 1s contains 2, 2s contains 2, which leaves 6 left to place. 1, 2, 3, 4, 5, 6. So when you do anions, your last orbital should contain a complete set of electrons. Okay, energy level diagrams for cations. So draw the energy level diagram for the atom first. Now, the electrons are removed. The electrons are removed from the orbitals with the highest principal quantum number. First. So this is very important. You remove the electrons from the orbitals that have the highest principal quantum number. So you know that on the labels from the orbitals, that's the number in front. So if we do the energy level diagram for nickel 3 plus, actually let's do nickel 2 plus. So 1s, 2s, 2p, 3s, 3p, 4s, 3d. So these are your inner electrons down here. So you can whip through these. Now, like we saw before, there were 10 electrons placed after this 18 had been placed. 2 went into 4s, and then 8 went into the 3d. But where will these 2 electrons come from? So we lose 2 electrons. They will actually come out of the 4s orbital because that has the highest principal quantum number. So we lose 2 electrons from there. and the others remain. If we were going to form the nickel 3+, we would actually remove the last electron filled in the last set of orbitals, so the last sublevel, which would be the 3D. So we would lose that electron there. Okay, now we're into electron configurations. Energy level diagrams are great, but they take up a lot of room. So an easier, faster method of showing the location and number of electrons is using electron configurations. And this is basically, you convey the information, it's the same information, horizontally. So, for example, carbon. Carbon has 6 electrons. So, you write the element, you write a colon, and then you start labeling your orbitals in the order that they increase in and how many electrons are in it. So our 1s orbital comes first, and it has 2 electrons in it. That's followed by the 2s orbital. The 2s orbital, which has 2 electrons in it. There's 2 electrons left to place. They go in the p orbital. So, the order of increasing energy goes to the right rather than up, as it does in energy level diagrams. And here we have the type of orbital, and the number of electrons. So if we were going to do nickel in electron configurations, and if you take a look at your energy level diagram, we have nickel, colon, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. And then the nickel 2+ will be 1s2, 2s2, 2p6, 3s2, 3p6. There is no 4s2 because that's where the electrons were removed from. It's just followed by 3d8. There is a shortcut that we can use for this method too. There's a shortcut method, and this is to replace all the information prior to the valence shell by that noble gas. So, if you look at nickel, on the periodic table, you put your finger on nickel, that's row, that period is its valence shell. The row or energy level before that ends in argon. So we can replace the electron configuration that is argon with argon. So what that looks like is nickel is now square brackets argon 4s2 3d8, and nickel 2 plus is argon 3d8. If we were going to do carbon, we would replace the 1s2 with helium. So carbon was 1s2, 2s2, 2p2. You could replace the 1s2 with helium. Not really a savings on that one, but that's basically how it works. So what I'd like you to do now is pause the video and write the electron configuration for sulfur both ways, without the shortcut and with the shortcut. So pause the video. Okay, sulfur has 16 electrons. So 1s2, 2s2, 2p6. Put your finger on sulfur. Where it actually ends is the last set of orbitals, so it's on the third energy level, and it's in the p block, so you know you've filled up to the 3 p's, and you're 4 elements into, or 4 boxes into the p's. So it's 3p4. The short form would be neon, because neon is represented by that electron configuration, and then 3s2, 3p4. Now do the electron configuration for manganese. You can pick which method you want. Pause the video and try it. So there's the long form and the short form for manganese. What I want you to do now is predict the electron configuration for both chromium and copper. And we'll take those up in class. Magnetism. Magnetism has to do with whether or not orbitals have paired or unpaired electrons. Paramagnetism is strongly magnetic, and it occurs in iron, cobalt, and nickel. So their electron configurations are I'm going to do the short form. So iron has 4 unpaired electrons. Cobalt has 3 unpaired electrons, and nickel has 2 unpaired electrons. So these atoms are fairly small, closely packed with domains that can align themselves in the presence of a magnetic field. So atoms are relatively small, closely packed, with domains that can align themselves. Oops, I combined 2 words there. That can align themselves in the presence of a magnetic field. So ferromagnetism is based on a collection of atoms. A whole bunch of atoms. Melting will destroy the domains and therefore the magnetism. So if you melt iron, it loses its magnetism, but as it cools and reforms, it will gain its magnetic properties again. Paramagnetism means weakly magnetic, and it's based on individual atoms. With unpaired electrons. So ferromagnetism is a collection of atoms. Paramagnetism is based on individual atoms. And then dimagnetic substances. So an example of a paramagnetism would be silver. Dimagnetic substances have no unpaired electrons. They're all paired up in orbitals. So they have no unpaired electrons, therefore not attracted to a magnet. It's all because of where these electrons are, where they're situated in orbitals.